So in this video, I'm going to expand 2 plus 2i to the power of 9. So we can see clearly inside here we're into complex analysis with the 2i in there. Now we can expand this out like we would in real analysis. So remember, in real analysis, if we want to expand, we have a plus b to the power of n. Expanding that out will be the sum of k equals 0 to n, so there's this n. We'll have n choose k and then multiply by a to the power of k and b to the power of n minus k. So that would be sufficient to expand that out if we wanted to, and that would give us n plus 1 terms. So in that expression here we'd have 10 terms, so it's going to be quite a lot of work to expand that out. Now what we can do with complex analysis, as is always the case with complex analysis, there's shortcuts to get us to our answers quicker, and this is also the same kind of situation. So with complex analysis we can always break this down into a couple of parts. We could break it down into a radius and a argument. So first of all, let's draw this on our Argand diagram. So that's our real, that's our imaginary. 2 plus 2i, so the real component is 2. So that's 2. And the imaginary component is 2i. So it's also a positive, but in the 2i's. So that's 2i. So what we can do now, we can calculate the argument, in which case we'll calculate the principal argument, because there is infinite solutions to the argument as we keep rotating round. So the principal argument, let's call it theta, and we want the radius. So to do that from our input, that's what we can do first. Now to find the input, all we need to do now is r would be square root of 2 squared plus 2 squared. That's our real and imaginary coefficient. So that's going to give us square root of 8, which is 2 root 2, or you might want to call it 2 to the 3 over 2. So that's our radius. And then our angle theta, that's just going to be inverse tangent of our imaginary component, which is 2, and our real component, which is 2. So pretty straightforward, inverse tangent of 1, that's going to give us pi over 4. So that's our angle theta. So now our building blocks for this, we've got theta's pi over 4. So let's put our theta there. And our radius is this value here, 2 to the power of 3 over 2, 2 root 2, whichever one you want to choose, they're all the same. So now what we can do is we can use DeMoivres theorem. So we can express our imaginary number. So DeMoivres theorem, I'll just put it like that for short. So what that we can express that as z to the n, and then what we can do is, using our building blocks, use the classic situation, r to the n cosine theta times n plus I sine theta n, and that's the input of the cosine. That's not cosine theta times n. So that would be using our theorem there. So now we've got this set up in this kind of format. Z would be our complex number. So Z in this case is 2 plus 2i. So we've got that. N is going to be 9. So we've got that. Our angle theta, that's pi over 4. So we've got all the building blocks that we need with our radius. So the radius is 2 to the 3 over 2. So what we could do is we could transfer that into this theorem, and let's see what that throws out to us. So now from that, 2 plus 2i to the power of 9, using that into that, that would equal our radius to the power of 9. So 2 to the 3 over 2 to the power of 9. So that takes care of that. and then we got cosine theta times n. Well, theta is pi over 4 times 9, so that's cosine of 9 pi over 4. So that takes care of that. Then obviously the argument for sine is going to be the same with the imaginary constant in front of it. Okay. That is much easier to work with than that. This is going to get us there much quicker. So now 2 to the 3 over 2 to the power of 9. That's the square root of 2 to the 27 basically. So if I write 2 to the 27, that will be that. 3 9s are 27, and then I've got the square root inside there. And then cosine of 9 pi over 4. Well, we could simplify that, because if I did 9 pi over 4, I would come back round one rotation and one more rotation. I'll be back to where we started from. So the equivalent to that is still going to be cosine pi over 4. So let's write that as cosine. Let's get it correct. And then I sine pi over 4. Okay, so that's kind of a setup for us for our result. Now, square root of 2 to the power of 27, that's going to give us 8,192 root 2. So I'll let you check that. 8192 times root 2. So basically it's 2 to the power of 13 plus another root 2 on top. And then we've got cosine pi over 4. Well, cosine of pi over 4, we know is root 2 over 2. So that's root 2 over 2 plus I. And then sine of pi over 4 is also root 2 over 2. So we could get this back into this format by using this formula. Now, as we've got root 2 here, I can distribute that with both of those and leave this 8192 out there. So I've got 8192, and then we're going to have 2 over 2, which is 1, plus I times 2 over 2, which is also 1. So 8192, 1 plus I. So that'd be one way of expressing our result. That is also valid. This is also another valid way of expressing our result in terms of sine and cosine. And then we've also got our exponential version. So if we write this in terms of e to the z, so here we got e to the pi over 4. So that would be e to the I pi over 4. So I've got e to the I pi over 4. So then I can exchange that and plug that into there. And then I'd have to go back with this value. So then that would lead me to 8192 root 2. So I'll put that in a bracket. And I can bring this out to the front if I like. So e to the I pi over 4. So that is also a way of expressing our result. So there's 3 ways of expressing this, expanded out in nice short format. So 3 results there. I'd still be trying to calculate my 10 terms for this one if I was using our standard way from real analysis. Okay.